In the previous lecture, we have discussed ground state of Deuteron. In this discussion, we have got actually two important results. First one was the depth of the potential well, which was actually of 36 mega electron volt. And the another finding was the radius of the deuteron nucleus, which was found 4.1 FM. And this value of radius actually implies that the radius of the deuteron nucleus is much more greater than range of the nucleon-nucleon interaction, or you may say nuclear force. And so from this result we have concluded that the nuclear force is a short range force. And in that discussion we have actually assumed that the ground state of the deuteron is actually a purely S state, or you may say 3s1 state, where a spin of the two nucleons, that is neutrons and protons, was taken parallel. I have told you in that very lecture that there is no excited states of the deuteron. Actually, it is an experimental fact that no excited states of deuteron exist. So in this lecture, I am just going to explain this very important fact, or you can say the experimental finding that the excited states of the deuteron does not exist. It has no existence. We are going to examine this fact, and from this discussion we will also gather some important informations regarding the nuclear force. So as I have told you that experimentally there is no evidence of existence of any excited states of the deuteron. In the present lecture we are going to prove that for L not equal to 0, you can see that this L is equal to 0 for a state, but if we assume that L is not 0, and as L cannot be negative, so definitely L will be greater than 0. And when we say L is greater than 0 and L has only integral value, it means L will be 1, 2, 3, 4 and so on. So in this case, we have to prove that when L is not 0 or L is greater than 0, then there is no bond state of deuteron, or you can say no bond state of deuteron exists. We have to prove. We will prove actually in this lecture this very important fact. For our calculation, we will take the case just like the ground state of the deuteron, and we will assume that the potential is central. As I have assumed in case of ground state of deuteron, we will again assume that the potential is central and a square well type. It means what type of potential we have taken in the discussion of ground state of deuteron, we are going to again taking the same potential, that is the central potential and the square well type of potential, which was actually a spherically symmetric potential. We are going to take the same potential too for the discussion of excited states of the deuteron. Now, when you will use the variable separation techniques, see, just I have written for your convenience here that using separation of variable technique, the radial part of the Schrodinger equation on putting u of r equal to r into r of r is given as this, as I have written in equation 1. In fact, this equation has already found in the previous lecture for ground state of deuteron. Only the difference is that we have taken L equal to 0 for the pure S state, but here as our aim is to take the non-zero value of L, so we cannot take L equal to 0, but we leave the L as L, and we can take L equal to 1, L equal to 2 and so on. Now this equation is just equivalent to an S wave radial equation, if we will assume a potential, let's see here, if we assume that there is a potential which is equal to VR plus L into L plus 1 H cross square over MR square. It means the sum of these two terms is treated like a potential and we call it V effective. So if we treat the sum of these two terms as V effective, then this equation will be just identical to the equation for the radial part of the S wave. And so this is not very different from that equation. The only difference is that L is non-zero here. And this second term in the RHS of equation 1a, that is L into L plus 1 into H cross square over MR square, this is actually known as centrifugal potential. You can understand why this term is known as centrifugal potential. You know, in classical physics or in classical mechanics, we study a centrifugal force which acts on a particle moving along a circle in outside direction from the center along the radius. And whenever potential is differentiated with respect to a space coordinates, or you may say simply a space, then we get the force. So see the form of this potential, and you can see if we will take the space derivative of this very potential, we simply get a force like term, and that force is nothing. This is actually classical centrifugal force, and this is the reason this term is known as centrifugal potential. So for your convenience, I am just writing it in very short, that the space derivative of L into L plus 1 times H cross square over MR square gives the classical centrifugal force. So it is called centrifugal potential. One more thing is here remarkable, that this potential is actually of repulsive nature, or you can say that this potential is repulsive, and so as L will increase, the binding energy of the lowest bond state will decrease. So this is another remarkable fact regarding this potential, that it is repulsive. It is means this centrifugal potential, this is repulsive, and this implies as L increases, the binding energy of the lowest bond state decreases. So if we consider that our lowest state is not actually L equal to 0 state, but it is L is not equal to 0 state, you can take L is equal to 1. I am not giving a particular value of L, but it is understood that L is not 0. So for the state L not equal to 0. You can say that this L is say 1. The binding energy is EB dashed. As I have assumed that the binding energy of deuteron nucleus in ground state was EB, and that EB was what? That was 2.226 MeV. So in this case you can say that this EB dashed will be definitely less than this much, but what is its exact value I don't know here, and there is no need to figure out its actual value. So we can only say that this EB dashed will be less than 2.226 MeV. So see this figure. Here I have plotted the square well potential, that is V of R in against of R, and in this figure the level of total energy, which is equal to in fact negative of the binding energy. I have written the binding energy equal to EB prime, not EB, because in this case definitely the value of binding energy of the deuteron nucleus in L equal to not 0, L not equal to 0 state will be definitely something smaller than its ground state binding energy, that is 2.226 MeV. So in our present discussion we are taking that EB dashed is the binding energy of deuteron in L is not equal to 0 state. So the only difference will be that where we have taken EB in the case of ground state of deuteron, you have to take EB prime at that position. So now we will see this equation 1 when we will apply for the square well potential. So see first of all the definition of this potential, that the square well potential, how it is defined. So the square well potential is defined as, the definition is same. You know V of R is equal to minus V naught. You know where V naught is actually depth of the potential, and this is for R less or equal to R naught, and this equals 0 for R greater than R naught. Just this definition we have already seen in case of ground state of deuteron. You can see here at between the point R equal to 0 to R equal to R naught, in this range the potential is what? The potential is fixed at the value minus V naught, and for R greater than R naught it is throughout 0. So this is the definition of the square well potential, and now we will apply this equation 1 for this square well potential in the two regions, that is inside the well and outside of the well. So you can write that equation. So equation 1 for R less or equal to R naught is given as, see, d2 UL One thing more is remarkable here, that here u has been written ul because here L is not equal to 0. So this is the wave function when L is not 0. So the symbol has been changed. So d2 ul by dr square plus, if we multiply by the factor m over h cross square into the inside terms, what will be the result? So this will be e over h cross square, and see here e is equal to minus eb dashed and v of r is equal to minus v naught inside the well. So this will be actually v naught minus eb dashed. We have just combined these two terms and minus the centrifugal potential term. This will be actually L into L plus 1 over r square. Here m over h cross square will cancel out, and ul, this is equal to 0. Now this constant term is we can replace by k square, as I have done previously. So this will be d2 ul over dr square plus k square minus L into L plus 1 over r square into ul equal to 0. And say this is equation, that was equation 1a, and now say this is equation 2. And you can see what does that term k means. We can see here that where k is equal to a square root of what? M into v naught minus eb dashed over h cross square. This is just a positive constant. And this equation 2 is for the region inside the well. So you can write the condition that when r is less or equal to r naught. You know this r naught is actually the range of the nuclear force or nucleon potential, because you know the square well potential, in case of a square well potential, it has non-zero value in this range, and outside of this range this potential is 0. So this is actually the Schrodinger equation for the region inside the square well. Now the solution of this very important differential equation is actually in terms of a spherical Basal function. I do believe that you have definitely done the course in mathematical physics on Basal's function, particularly the spherical Basal function of first kind and second kind. Actually, the spherical Basal function of second kind is also known as Newman function. And if you are remembering those Basal function, then it is okay. And if not, I would like to suggest you, before going to this lecture, you should consult the topic on spherical Basal function, and after that the discussion which I am going to provide you in this lecture will be very easier to understand. So, but here I am just writing the solution of this equation. You can see the solution of this equation 2, actually in its solution, the spherical Basal function, which is denoted by JL, and the spherical Newman function, which is denoted by NL, which is also called second kind of Basal function, will be involved. So you can say the general solution of this equation 2, that was equation number 2, involves a spherical Basal function. And this spherical Basal function will be denoted by JL. Remember, this is a small j, JL. And a spherical Newman function. Newman function, and this is denoted by the symbol NL. Actually, this Newman function is also called second kind of Basal function. Now, an important property of this Newman function is that the value of this Newman function NL tends towards minus infinity when r tends to infinity. When r tends to infinity, in that condition, the value of this Basal function of second kind, or you can say that NL tends to minus infinity as r tends to infinity. And so the solution of this equation here, this equation means equation number 2, can be written as, so the solution of equation 2 is, this solution will be written as UL of R is equal to A JL of KR when R is actually less or equal to R naught. And this is equation, let us say 2A. Here A is an arbitrary constant, an arbitrary constant. And this JL of KR, this is actually the spherical Basal function, and how this spherical Basal function is defined. So you can say where this J of KR, actually in original definition in mathematical physics, here is a term which is written as rho, but in present case rho is equal to KR, so I am just writing it KR. This JL of KR is equal to pi over 2 kr to the power half j. Remember, this is capital J. It is different from the small j. L plus half of kr. This is 2b. In this equation, this jl plus half of kr, it is actually Basal function of half odd integer order. This j of l plus half, jl plus half, what is this? This is called Basal function of half odd integer order. Actually, L has integral value, so when we will add 1 over 2 in L, there will be a number which will be odd half integer, and so this is called Basal function of half odd integer order. And so this is the solution of the equation for the interior of the well, that is in the region R less or equal to R naught. Now actually we will apply that Schrodinger equation for the region outside of the well, that is when R is greater than R naught, then equation 1 will be what? In context of the square well potential which we have assumed. You know, when R is greater than R naught, then what is V of R? You can see that in a case, in the definition of a square well potential, when R is greater than R naught, that is R is greater than the range of the nuclear force, then this V of R is equal to 0. And when V of R will be 0, then what will be the form of equation 1? So, in this region, equation 1 is given as. How we will give equation 1? This will be d2ul over dr square. See equation 1, there was a factor outside of the square bracket m over h cross square. Now I would like to multiply it to the interior terms. So in the interior there will be minus MEB dashed over h cross square. You can see here was the term E, and E is equal to minus EB dashed. So this will be minus MEB dashed over h cross square, and minus L into L plus 1 over R square times UL, and this equal to 0. And we can take the negative sign as a common factor in for the terms inside the bracket, and after that what will be our result? So this will be minus. Now take this constant as gamma square, as I have taken it gamma square in case of ground state of Deuteron. The only difference is that here EB has been replaced by EB prime, but in spite of that I am taking it as a constant gamma square, and plus L into L plus 1 over R square. times UL, and this equal to 0. And what will be the equation number? So let us say this is equation 3. And you know this equation has been written for the region outside of the well. That is, this is for R greater than R naught. You may use the term of equality here or not. They refer the same thing. And so this is equation for the outside region of the well. Now the solution of this equation, but first of all you can see here what is the constant gamma. We have written gamma at the place of a square root of MEB prime over H cross square. This is actually gamma. Now, as I have told you that the equation of this form has a solution in terms of the Basal function, and so its solution is written like this. The difference between the equation 2 and equation 1, equation 3 is what? In this case, here minus sign is present, so there will be a difference in solution. The solution of equation 3 is given as, this is given as UL of R equal to, here we take another arbitrary constant B instead of A, and HL of I gamma R, and say this is equation 3A. Here again this B is an arbitrary constant, and what is this HL of I gamma R? Actually HL of I gamma R is the combination of the Basal function of first and second kind. How it is defined? So you can see where this HL is equal to JL plus I NL. You know this JL is a spherical Basal function, and this NL is a spherical Newman function or Basal function of second kind, and this HL is this combination of JL and NL. So you can see that this HL is actually a complex function. So the Newman function NL, how it is defined? As we have already seen the definition of JL, but what is the definition of NL? So if we know the definition of JL NL, we can find HL. So here NL of R, this is NL of not R, but NL of I gamma R. See here, I gamma R. This is actually defined as minus 1. This is defined as minus 1 to the power L plus 1 into pi over 2I gamma R whole to the power half, and capital J minus L minus half of I gamma R. This is the expression by which we define this Newman function, and say this is equation number what? This is equation number 3b. This is 3b. Now we have seen the solution of the Schrodinger equation inside the well and outside of the well when L is not equal to 0. Now to find the constants, arbitrary constants, we apply the boundary condition always in quantum mechanical problem. So here are the two boundary conditions, and you can see by combining that two boundary conditions we can express only one boundary condition. So now the boundary conditions are what? The boundary conditions are, actually the first boundary condition we can apply is, you know that the wave function or eigenfunction UL of R is continuous at the boundary. And what is the boundary? Boundary is R equal to R naught, because you know this point R equal to R naught, actually not point but a plane passing through R equal to R naught actually divides this region in two parts. The first region is between 0 and R naught, and the another region is from R naught to infinity. So at this boundary, definitely the wave function UL of R should be continuous, because it is a important characteristic of the valid wave function. And again, the first order space derivative of the wave function is also continuous at the boundary. So the another boundary condition will be dUL of R by dr is continuous at R equal to R naught. Actually, these are the two continuity conditions for the valid wave function, that is UL of R. But we can actually express these two conditions in a single condition. I am just writing it for your convenience that these two conditions may be combined. Into one condition. And actually, what will be that one condition? That one condition will be actually what? This is the logarithmic derivatives are continuous at the boundary. The logarithmic derivatives are continuous at the boundary. Boundary means R equal to R naught. R equal to R naught. And how we will express this boundary condition that the logarithmic derivatives are continuous at R equal to R naught? How we will express it mathematically? One over UL dUL by dr. In fact, this is for the inner part of the well, is equal to 1 over UL dUL by dr outer. And say this is equation 4. This is equation 4. Now, in you can see that in equation 2, perhaps 2, here see, this is equation number 2, 2a. UL is defined here for the region R less or equal to R naught, and in equation equation 3a, UL is again defined, but this is for the region R greater than R naught, that is outside of the well. So substituting the value of UL for the inner part of the well and outside of the well in this equation, what we will get? So you can say that applying apart from this, we should also note here one of the important property of the Basal function, or you can say the property of derivative of Basal function. So one of the important property of Basal function is, this is for derivative of the Basal function, dj L of rho by d rho. This is actually equal to j L minus 1 of rho minus L plus 1 over rho JL of rho. This is actually an important property of the Basal function. Say it is 4a. Now, using this very important property of Basal function and equations as you have seen, 2a and 3a. So you can say applying this property in 5, not in 5 but 4. In 4, this is equation actually 4. In 4 and using equation 3a, not 3a but 2a, and 3a, we will get, see what is equation actually 2a. Actually 2a is 2l ul of r equal to what? This is a times jl of kr. You can see this result in equation 2a. This is 2a. ul of r is a, jl of kr. And you should note that this is for the inside region of the well. So if ul of this much is a, jl of this much, so what will be dul by dr? this will be actually Ka dJl of Kr by dk of r, and when actually this k is y, when we will differentiate k of r, k into r with respect to r, that will be k. And similarly, you have seen that in equation number 3a, that UL of R outside of the well is B into HL of I gamma R. So you can find from the equation 3a. From 3a, UL is equal to B HL of I gamma R, and therefore what will be DUL by DR? This will be actually I gamma B DHL of I gamma R over D I gamma R, D I gamma R. And so you can see, if we will put this value of the Basal function in the equation which is defined in this property. So this, as derivative of JL of rho with respect to rho is this much, so we can put the value, we can use this result to simplify for this term and for the simplification of this term. And so from equation, what is that equation? The equation is actually 4. So you can write from 4 that K, do some algebra which I am just leaving here for the sake of time. So K, this will be J L minus 1 of KR over JL of KR minus L plus 1 over KR, and this is equal to I gamma HL minus 1 of I gamma R over HL of I gamma R and minus L plus 1. This is actually L plus 1 over I gamma R. And this is at R equal to R naught, and this is also at R equal to R naught. but this is inside the this region is inside the well and this is outside of the well. Now you can see from this result that this, if we multiply by the factor k, what will be the result? This is k into JL minus 1 of KR over JL of KR minus, and the in second term k will cancel out and this will be simply L plus 1 over R, and this is equal to, when we multiply by the factor I gamma, so write it as gamma into IHL minus 1 of I gamma R over HL of, this is HL of I gamma R and minus, here I gamma will be cancel out and this will be L plus 1 over R. But see here, as R is equal to R naught both sides, so we will replace the R by R naught in every term. So there will be R naught. This is R naught, this is R naught, and this is R naught. Everywhere there will be R naught. Now you can see these two terms will cancel out. So these two terms in LHS and LHS are cancel out, and what will be our result? Actually now we can write this equation as, this implies JL minus 1 of KR naught over JL of KR naught. This is equal to gamma over K into IHL minus 1 of I gamma R over HL of I gamma R. And what will be the equation number? Actually this is 4a, and you can say this is equation 5. Let us see. Now see this equation and particularly the RHS of this equation. Now you know this R, here is R naught, not R. We know that the range of the nuclear force is of the femtometer. So let us take a specific value R naught less than 1.43 Fermi or femtometer, and apart from this gamma into R naught is actually less than 1, and we know that this gamma is much smaller than K. These are known. So the expression inside this square bracket in RHS of equation 5 is also less than 1. So the term, not term but expression inside the bracket in RHS is less than 1. It is less than 1. So you can see that this gamma is much smaller than k, and what does it mean? It means gamma over k is much smaller than 1, and this term inside the square bracket is also less than 1. It means the RHS of equation 5 will be a very small number. It is just tending towards 0. And so to a first approximation, we can take that RHS of this equation is almost 0. So we can take the RHS of 5 to be almost 0. And if its RHS is 0, then what will be the result? Then this JL minus 1 times, not times, but JL minus 1 as a function of KR naught, this is almost equal to 0. JL minus 1 of KR naught is almost equal to 0. And say this is 5a. Now see this equation and let us find value of this function for a particular value of L, that is the lowest excited state. And what will be the lowest excited state? That will be corresponding to L equal to 1, because you know after L equal to 0 represent the ground state, so the next value of L will represent the condition for the lowest excited state. So this condition will hold for all values of L, and we are just applying for L equal not all value of except L equal to 0. This equation will be valid for all values of L. So you can say that this condition holds for all angular momenta except L equal to 0, and for L equal to 1, and this is the lowest excited state. Lowest excited state. Here I have written EXST, this is for excited state. And L will be 1 for the lowest excited state, and for this, what will be this result? As the term is JL minus 1 and here L is 1, so this will be 0. L minus 1 will be 0. So J0 of KR naught, this will be almost equal to 0. And say this is equation 5b. But from the property of the Basal function, you have, if you have studied it, definitely you have been found that this J naught of rho is actually equal to sine rho over rho, and at the present condition in place of rho is KR naught, so we can say that J naught of KR naught, this is equal to sine Kr naught over Kr naught. So from equation 5b, see the equation 5b, we will have sine Kr naught over Kr naught almost equal to 0. And if sine Kr naught over Kr naught is 0, then what does it mean? It means sine Kr naught is equal to 0. And if sine Kr naught is equal to 0, what will be the values of Kr naught? The accepted value of Kr naught will be actually equal to plus minus pi plus minus 2 pi plus minus 3 pi and so on. See the value of Kr naught. Remember, mathematically, if we will take Kr naught equal to 0, even then this equation will be satisfied. But it is not physically possible because Kr naught cannot be 0 since R naught is not 0. It has a finite value, although it is very small, but it not 0. So Kr naught equal to 0 is not permitted here. So we can take only plus minus pi, plus minus 2 pi, plus minus 3 pi. When sine Kr naught is 0, then the value of Kr naught. And from this result, if we want to find the minimum well depth, for the calculation of minimum depth of the well, we will take the first value, that is plus minus pi of Kr naught. So for the minimum well depth, Kr naught should be taken as plus minus pi, and this implies K square R naught square will be equal to pi square. Now let us substitute the value of K square in this result. What we will get? This will be actually K square is m into V naught minus EB dashed over H cross square and times R naught square. This is equal to pi square. Just as I have taken the assumption in dealing with the ground state of Deuteron that this potential well's depth V naught is much greater than the binding energy of the Deuteron nucleus, and this assumption will be also valid here. So you can say this V naught is much greater than EB dash. So in a first approximation here, we can neglect this EB dash in comparison to V naught. And so under this assumption, our result will be mV naught over H cross square times R naught square equal to pi square. And therefore, what will be V naught? This V naught is pi square H cross square over m R naught square. Actually, this is the depth of the potential well which I have calculated in terms of the range of the potential R naught. So, if we take the value R naught equal to 2 Fermi, let us say 2 Fermi. Actually, the experimental value of short range of nuclear force is of this order. So for example, if we take R naught equal to 2 Fermi, then what will be V naught? Then actually we will find that this V naught is equal to 144 MeV. Remember, in case of ground state of deuteron, in case of ground state of deuteron, for the bound state, V naught was almost equal to 36 MeV. But if there will a bound state, even when L is not equal to 0, then the potential well should be a depth of at least a depth of 144 MeV. Because if we will take the larger value of L, that is L equal to 2, L equal to 3, we will find that the deeper and deeper well depth can produce the bound state. So we conclude that there is no bound state, or you can say that no bound state exists for L greater than 0, because this much depth of potential is not practically possible. So you can say, so depth of well for bound state in the state L not equal to 0 is much greater than the well depth in case of ground state of deuteron. Ground state of deuteron. And from this, as I have told you, if you will take L equal to 2, 3, 4 and so on, the more deeper and deeper potential will be needed to create a bound state. And so we conclude that, our conclusion is that if L is not 0, then there is no bound state of deuteron. And so we can give the conclusion there is no excited states of the deuteron nucleus. And this was to prove actually in this lecture, and I hope you are now aware clearly that the excited state of deuteron does not exist. Now in very brief, we can draw the informations regarding the nuclear force which we have learned from these two theories, that is the ground state of deuteron and the excited state of deuteron. So what are the remarks? Remarks about the nuclear force. Remarks about the nuclear force. First of all, you can see that in the theory of ground state of deuteron, we have seen that the neutron and proton can form a stable combination only when the spin of the nucleons are parallel. That is, they can form a stable combination only in triplet state, or you can say 3s1 state. So N and P can form a stable combination only in triplet state. Triplet state has a spectroscopic symbol 3s1 only in triplet state, that is in the state of parallel spin. Actually, this state is represented as Kate. The parallel sign is written inside the Kate. The another remarkable fact is that the singlet state, which is actually denoted by 1s0, in this state the NP spins are anti-parallel, and this is not a stable combination, and you can say this state is actually unbound, not a bound state. So the singlet state 1s0 NP spins, neutron proton spins, are anti-parallel, and this state is represented like this. And the system is unbound. System is unbound. Again, we have seen that the total magnetic moment of a deuteron nucleus is not zero, and its quadrupole moment is also non-zero. Both of them are non-zero. The non-zero value of the magnetic moment and quadrupole moment of deuteron actually gives an information that a part of nucleon force acting in the nucleus of deuteron must be non-central, that is tensor force. So mu, this is actually the total magnetic moment, this is non-zero, and QD is quadrupole moment, this is also non-zero. Non-zero values of these two quantities reflects what? Actually it reflects that a part of nuclear force in deuteron nucleus is non-central or tensor force. The another remarkable fact which we have drawn from the theory of ground state of deuteron is that we have found that the radius of the deuteron nucleus is greater than the range of the nuclear force. What does this refers? Actually, RD greater than R0 indicates that nuclear force is a short range force, because we know that the nucleus of deuteron is not a tightly bonded system. It is barely a loosely bonded nucleus, you can say, or you can say that neutron and proton are loosely bonded in the deuteron nucleus, and so it refers that nuclear force is a short range force. So this Rd greater than R naught implies that nuclear force is of short range nature. Short range nature. So this is all about the ground state of deuteron and excited state of deuteron. We have found that there is no excited state of deuteron. This is a very remarkable fact.